Okay, this is going to be the continuation of the video that I started earlier regarding our semester exam review. Picking up with physics, Newton's laws. Newton's laws are laws that govern the motion of all objects in the universe. And so there are three of them. Newton's first law is the law of inertia, states that objects in motion stay in motion, objects at rest stay at rest unless acted on by an outside or an unbalanced force. So an example of an object at rest remaining at rest would be if you pull a tablecloth out from under a set of dishes or a table full of dishes, the dishes will remain at rest. The reason for that is because of inertia. Another example of an object in motion staying in motion would be in a car crash. If you're not wearing your seatbelt, your body continues to move forward because no force is acting on it. The exception would be if you're wearing your seatbelt, in which case there would be a force acting on your body. It would push you back into your seat. And here I have a little picture of a skateboarder that ran their skateboard into a curb, and you can see that the skateboard has a force acting on it, so it stops. And the person does not have a force acting on them, so they continue forward at a constant
Lisandro
rate.
Sosa, please come to the reception desk. Lisandro Sosa, to the reception desk.
Newton's second law states that force is equal to mass times acceleration. Another way of thinking about that is acceleration depends on both mass and force. So if you increase the amount of force applied to an object, you're going to increase the acceleration. And if you increase the amount of mass, like for example in the picture there, it's going to decrease the acceleration of the object. So this is kind of like the potato lab we did, where a smaller potato went farther than a large potato, and when we pumped it more full of air, it went farther because there was a greater force. Newton's third law states that for every action there is an equal and opposite reaction, or for every action force there's a reaction force that's equal and opposite. Here's a picture of basically a book sitting on a table. The weight pulls down on the book, and that's due to gravity. And then there's an equal and opposite force pushing back up on the book by the table. So because those forces balance out, the net force would be zero, and there is no acceleration. Another example would be bouncing a tennis ball off of a wall. The action force is that the ball applies a force to the wall, and the reaction force is that the wall pushes back on the ball. That's why it would, of course, bounce. So that's it for Newton's laws. The next section I have here is talking about force equals mass times acceleration. Just being able to calculate that. As a reminder of units, these are all different types of units. If you see these units in a problem, you should be able to identify which of these pieces of information is given to you. So force is measured in newtons. Mass is measured in grams, kilograms, or milligrams. They all have in common the word grams. And then acceleration is measured in meters per second squared. So here's our triangle that we set up. Force is on top, mass is on the left, and acceleration is on the right. The equation, again, F equals ma. So we multiply if we have the bottom numbers. And if we're solving for mass or acceleration, then we'll, of course, take the force and divide it by the other. So, for example, mass would be force divided by acceleration. Acceleration would be force divided by mass. And then force is just mass times acceleration. So you multiply the bottom ones. If you're given force, you have to divide. Here's an example problem for you. Mr. Turner gets hit by a car with a force of 1,200 newtons. His mass is 80 kilograms. What is his acceleration? So we plug that number in. Force was 1,200. This is called our givens. My mass was 80 kilograms, which is a little bit more than what I actually am. And then the acceleration, we don't know. So the second part is our triangle. So we'll go ahead and fill that in. We know that force goes on top, 1,200 newtons. We know the mass goes on the left, is 80. And the acceleration, we don't know. And then step 3, we solve. So 1,200 divided by 80. And that gives us a, what is that? An acceleration of 15 meters per second squared. There's our answer. Here's another example problem. How much force would it take to accelerate him by 20 meters per second squared? So again, we're given the mass of 80 kilograms. And we don't know the force, that's what we're solving for this time. And we do know the acceleration is 20 meters per second squared. So we'll plug those numbers into our triangle. We got 80 for mass, 20 for acceleration, and we're trying to find force. So then when we solve, force is equal to 80 times 20, and that gives us 1,600 newtons since we're force. So that's just a real quick explanation about how to solve for F equals ma. The next thing we're looking at here is balanced and unbalanced forces. There's a key difference between balanced and unbalanced forces in that balanced forces kind of look like this. We've got an 8 Newton force to the right, 8 Newton force to the left on an object. So because those are equal, they cancel each other out. Since they're opposite directions, we subtract. So 8 minus 8 equals 0 newtons of force on that box. So the net force would be 0. If you plug that into our triangle, 0 newtons, the mass was 5. We can calculate the acceleration of the object. The acceleration is equal to 0 divided by 5. So the acceleration is 0. In other words, this object does not accelerate because the net force was 0. No force means no acceleration. On the other side, we've got an unbalanced force here. 8 newtons to the right, 4 newtons to the right. That's a total of 12 newtons to the right. We add those since they're in the same direction. We've got 9 newtons to the left. So then we take those, since they're in opposite direction, 12 and 9, and we'll subtract. 12 minus 9 equals a net force of 3 newtons on the box. And then we've got our equation again, F equals ma. So we can solve for that. 3 is our force. The mass is still 5. And the acceleration we don't know. So acceleration is equal to 3/5, which in fractions, if you were to convert that to decimals, would be 0.6 meters per second squared. 0.6 meters per second squared. So that's just a quick explanation showing you that if we have an acceleration, this one was 0, this one was 0.6, that means the object, the box or whatever, will accelerate. And we know that because the greater force is to the right, we can expect the acceleration of the box to be to the right. Just balanced forces, we know net force is 0. Unbalanced is greater than 0, as we demonstrated above. Object motion, no acceleration. And we do have acceleration with unbalanced forces. Roller coaster going down a hill. We know the forces are unbalanced because it's going to be speeding up. Book on a table. The forces are going to be balanced because it's not changing its motion. It's not accelerating. It's not speeding up, slowing down, or changing direction. Number 3, car going 20 miles per hour east. Doesn't say it's changing, so we're not speeding up, we're not slowing down, and we're not changing our direction. It's just going in one direction, constant motion. So this would be balanced. So we said this one was unbalanced. This one was balanced. We said the car going 20 miles per hour east was balanced. A car stopping at a red light. Because it was in motion and now it's stopping, we're slowing down. So that is acceleration. Acceleration is caused by unbalanced forces. And then last but not least, number 5, a ball is thrown up and then it comes down. That would be unbalanced forces because when it's thrown up, it's slowing down by gravity. Gravity pulls it back down. And then as it comes back toward the earth, it's speeding up due to the acceleration of gravity. So we have actually all 3 ways that it changes velocity. It speeds up, it slows down, and it changes direction in that example. Continuing on with speed, velocity, acceleration. Speed is the distance an object travels per unit of time. An example would be like 5 miles per hour or 5 meters per second. I didn't say which direction it was. It could be that way or it could be that way. And so either way, if it's 5, it's going to be the same speed. So these guys have the same speed, even though they're going in 2 different directions. This velocity is speed in a given direction. It's different. So for example, if it was 5 miles per hour west, that'd be different than 5 miles per hour east. So here's our guy going west. Here's our guy going east. And they have different velocities. So up here we saw the speed was the same. Down here we have different velocities because they're going different directions. Last but not least, we have acceleration, which is change in the velocity of an object. There are 3 ways it can do that. Speed up, slow down, or decrease in speed, and the object can change direction. Those are the 3 ways that an object can change velocity, because velocity is speed in a given direction. So here we have a picture, and just a quick example here. We have the ball that's being kicked in the air. We can see that it's constantly changing its direction, but we'll say that for a minute. As it goes up in the air, it's slowing down, decrease in speed. As it reaches the top, instead of going up, now it begins to go down. So we have a change in speed, or change in, direction. And as it falls, it begins to increase its speed back toward the earth. So that's a good example showing all 3 ways that the velocity can change. That's a good example of acceleration. Speed calculations. So speed is equal to distance divided by time. The only way to do it with the triangle is to do speed on the left, distance on top, and time on the right. So speed equals distance divided by time. So just to give you an example about how to calculate that, an object travels 15 meters in 5 seconds. How fast did it go? We have 15 meters would be our distance. Time, 5 seconds. And then we're trying to find our speed. So we plug that into our triangle. We don't know what the speed is. We do know distance was 15. We know the time was 5. So the step 1 given, step 2 triangle, step 3 solve. 15 divided by 5 is equal to 3. And our units, since we're solving for speed, are whatever we started with, meters and seconds. So it would be meters per second. Another way of thinking about that is the object travels 3 meters every second that passes. So if it was 5 seconds, we would end up with 15 meters of distance. Next part says, what if it only went 1 meter per second? How long would it take? So again, step 1 givens. We're given speed this time, 1 meter per second. And we're still trying to find how long it would take for 15 meters. So this one we're solving for time. Step 2, triangle. Speed was 1. Distance was 15. Time, we don't know. So time is equal to 15 divided by 1, 15 seconds. And last but not least, here we have an example with a graph. And the graph shows distance versus time. Let me bring this back up because this is going to fall. The graph is showing distance versus time. So if you were given a graph like this, you could find or calculate the speed, average speed. We can see it's changing because the slope is changing. It's not a straight line. Average speed is very simply just total distance divided by total time. So our total distance here was 18. Our total time was about 6 seconds. So we write our givens. We don't know speed. We're trying to find that. Our distance was 18 meters. Our time was 6 seconds. So step 2, triangle. Plug those numbers in. Distance was 18. Time was 6. And we're trying to find speed. Solve it. Speed is equal to 18 divided by 6, which is equal to 3 meters per second. So this is the way to find average speed on a graph, using information from the graph. last but not least, this is the very last one that we have. Explaining speed, velocity, acceleration in graphs. Constant motion means no change in velocity, speed, or direction. And the forces for that would be balanced. We talked about that earlier. So constant motion, balanced forces, no acceleration, zero force. And examples of that would be an object going fast versus an object going slow. Constant speed. How do we know they're constant? Because they're straight lines. This one's faster than that one because the distance increases at a faster rate than this one. Another example would be if the line is horizontal like that, no slope means no speed. It's not moving. It's not changing its distance from where we started. So the distance remains constant. Changing motion is changes in velocity. There are three ways velocity can change. It could increase speed. I've already said this. Decrease speed. Or change direction. And so to demonstrate those on a graph, an increase in speed means that the slope of the line increases. So there's our point of unbalanced forces occurring. We have our acceleration occurring at that point. So this would be increased speed. A decrease in speed would look like that. So we start off with a steep slope, and then we end up with a slope that is more flat, more horizontal. And then changing direction would look something like that. Here's our point of accelerations. So we know that the forces are unbalanced at each of those points. Otherwise, the forces are balanced because there's no acceleration occurring here. This is constant because it's a straight line. But overall, looking at the graph, we do see acceleration occurring. Here's one final example. Explain the motion. Here we start off slow on 1. At point A, we can see that the slope increases. So that would be unbalanced forces at A. We do have an increase in speed. As it reaches B, instead of going fast, it stops from B to C. At C, we can see that it changes direction because our distance begins to decrease. And it does speed up in the opposite direction. I hope that you found this review useful. I'm going to try to get this posted by 7 o'clock tonight, so I hope you guys take the time to watch it before your review. If you have additional questions, please make sure you talk to your science teacher. Thank you very much.